All right, my C and D block classes. So I'm doing this in my office, and the fan, the incessant fan, is driving me a little bit crazy, and you're going to have to deal with it too. So tonight we're going to be talking about two concepts that are completely connected to one another. The first of which is something that we actually have looked at before, but we're going to look at it in a slightly different way: atomic mass. And then we're going to take it a step further and look at something called formula mass. Ooh, let me start that again. Now, the reason why we're going to be talking about these two terms is that we are very soon going to be moving into a concept called stoichiometry. And well, I have to change. This is too loud. Christmas music in the background. So stoichiometry is something that's very useful when you're doing experimental chemistry, and you need to predict the amount of something that's going to be produced in a chemical reaction based on how much you put in terms of the reactants. And most of the winter term, in fact, we're going to be talking about stoichiometry and the complexities associated with it. So if you're going to be measuring something, then obviously you need to know the mass of a particular element or compound that's going to be involved in your chemical reaction. And that's why we're starting with this concept of atomic mass and formula mass. So let's first establish something which is, I think, fairly obvious, but I think it needs to be stated. And that is that atoms, which we all know at this point, consist of three things. We have electrons. Oh, why the lowercase e, Chang? Okay, electrons, protons, and neutrons. And it shouldn't be too much of a surprise for you to know and understand that all three of these things, electrons, protons, and neutrons, have a particular mass. I mean, they're matter, so they're going to contain mass and volume for that matter. But what that means for you folks is that if each one of these things has mass, and it's a measurable mass, then all atoms have a mass that's unique to that particular element. And we understand that because, say, for example, we have something like the element oxygen, right? Oxygen's going to have, oops, there we go. Oh yeah, 6 electrons, 6 protons, and 6 neutrons in its most common isotope. Okay, and that would be different from, say, something like hydrogen, which only has 1 electron, 1 proton, and 1 neutron. So because each element is defined by the number of protons, right, associated with it, then each element's going to have their own unique mass. And we're going to call that atomic mass. Surprise, surprise. Now, if we were to, let's imagine then that these masses also have a unit. And in fact, the unit, which is a capital U, no, not a capital U, actually, it's a lowercase u, it stands for the term unified atomic mass unit. Used to be called just atomic mass unit, and it's largely the same as the old atomic mass unit, but it's a little bit more accurate nowadays when we call it unified atomic mass unit. And here's the thing. It's not really something that's measurable with a balance. You just can't. I mean, these are such tiny little things. It's not like you can put it on top of a balance and be able to measure it. And so it's a lot of math and theory and physics that goes into determining the mass of each one of these subatomic particles. And therefore, if it's all based on theory, then it's not really something that we've measured. It's more something that we've determined. Okay? So that means each of these things, each of these atomic masses is something that's been determined for each particular element. And to confuse things even more for you guys, let me just move to a new page. It's actually a relative scale that we use. A relative scale is used to measure the different atomic masses of all the different elements that exist. Now, that's different from what's called an absolute scale. In an absolute scale, it's something that's measurable, and everything has its particular mass. So, for example, if I were to take myself, right, and I put myself onto a scale, that would show me how heavy I was, it would come out to be 180 pounds. That's an absolute number, 180 pounds. All right, so we always know that a single Darren is 180 pounds. I know it fluctuates here and there, and it'll increase as I get older, but imagine that it's always locked in. Every single me is 180 pounds. Well, in the case of a relative scale, we're going to lock in on one particular absolute, and we're going to call that Darren, and we're going to measure everything relative to Darren. So let's say that we wanted to measure who's somebody who's tiny? A Delon, okay? So we take Delon. There's Delon. And we're not actually going to put Delon on the scale. What we're going to do is we're going to assess Delon relative to Darren, and we're going to figure out a relative mass for Delon. And in fact, we measure her, and we don't actually ever put her on a scale, but we measure her density, we measure the length of her arms, her height, everything that we need to measure. And from that, we know the arms and the density of Darren. We can then figure out Delon. But the key is that we actually figure out Delon relative to Darren. So she would probably be something like 0.68 Darrens. She's not 180 pounds. She's some fraction of me. And then we take somebody like Alexander, okay, who's bigger than I am, although my guess is he weighs less. But let's pretend, Alexander, sorry to make you a heifer. We take somebody like Alexander, and he's bigger than I am, and so, again, we do all those measurements, and relative to Darren, Alexander would be something like 1.23 Darrens. Okay? So that's essentially how we have to measure all the elements, except we don't measure it with Darren. Okay, that would be kind of cute, but we don't. We actually measure it with carbon-12. So carbon-12 becomes our standard, and everything else is based on how it is relative to carbon-12, whether it's going to be something that has more protons and therefore heavier, or fewer protons and therefore lighter. Okay? And it's very important, too, that you understand that carbon has many isotopes, but we're focusing in on the isotope carbon-12 for our relative scale here. Okay, so where do we get these atomic masses? Well, I think you probably already know this. If you look at, hold on, I'm going to pause for a moment. Okay, our best friend, periodic table. And if you look at the periodic table, you obviously see that there are numbers associated with each one of these elements. And it's the number that has many decimal places. And so if we look at carbon, we can see carbon has 12.011 unified atomic mass units, or U's. Oxygen has 15.99 U's. Nitrogen 14.07. And then if we were to cruise over to other parts, I guess I can't. Well, that's really sad. But you can see here, obviously, that silver has 107.868 U's. Now, the reason why they're not nice, clean numbers is because we also have to understand, as I mentioned before, that this is a weighted average of all the isotopes of that particular element. So in the case of carbon, because we have carbon-12 and carbon-14, a little bit of carbon-14 is going to make it a little bit heavier. All right? And obviously carbon-14 is fairly rare because it doesn't have that much of an impact on the atomic mass of carbon overall. All right. Now, the next question is, what do we do with this? Well, let's imagine we want to figure out the unified atomic mass for something like sodium chloride. It's a pretty easy thing to do here, because all you have to do is sum up all the atomic masses. So in the case of sodium, the atomic mass of a single atom of sodium is 27.990 U. The atomic mass of a single atom of chlorine is 35.453 U. And again, I just got that from looking at the periodic table. And because there's only one sodium and one chloride ion that goes with the single formula unit of sodium chloride, the mass of this whole, the entire formula unit, the formula mass, is 58.443 U. Okay? Similarly, let's say we go for something a little bit more complex. We take glucose. Okay? And glucose, now you have to take into account that there are subscripts here, but it's not that difficult to understand. All you need to do is make sure you take carbon, then since you have 6 of them, you're going to multiply 6 times 12.011, which is the atomic mass of carbon. And then you need to do the same thing for hydrogen, but there are 12 of those fellas. And hydrogen has a tiny atomic mass, right? Smallest that exists in the periodic table. And then we do the same thing with our oxygen. And again, I'm just getting these numbers directly from the periodic table. So when you do the products of all 3 of these, and then sum them all together, this will come out to being a formula mass for the molecule C6H12O6, or glucose, of 180.155 U. All right? Easy stuff, huh? See you tomorrow.